Depth quantization. For the quantization process, a depth can be approximated by a layer. The motivation of the idea was from the scalar quantization in compression. Via the quantization process, a coefficient can be approximated. In the process, the layer leaves a parameter. From the results in section 3.3.3, the histogram of the depths was calculated firstly. The representative, anchor, depth, A1, for layer 1 was always assigned as the minimum depth of all the depths. When the depths are partitioned into two layers, we propose the following optimization to determine the anchor depth of layer 2, A2. Where A2 is subject to A2 greater than Z greater than A1, for each Z in layer 1, and Z greater than or equal to A2, for each Z in layer 2. By recursively subdividing a depth layer to acquire two more depth layers, the procedure can be applied to acquire layers. The depths in the layer are updated to be the depth of the anchor if the anchor depth of a layer is determined. For instance, the depth Z in layer J is assigned as AJ. Hence, Z minus AJ for Z in layer J is the error in approximating Z with AJ. In the approximation, the anchor depth can be found from 20, which has the minimization of the error. By sampling a few depths as candidate anchor depths firstly, the anchor depth A2 in 20 can be derived. Next, we set each candidate as A2 to calculate the average error from 20. With the help of the histogram of the depth, this process can be efficiently achieved. So, the anchor depth is the depth in the candidate depth that yields the smallest average error. Shows the estimated depth map and the depth quantization results on an image, composed of 4 layers of depth. After quantization, some outliers in B are removed. A. The image composed of 4 depth layers. B. Depth map derived by multi-scale blurring and deblurring approach. The top 2 layers of depth can hardly be distinguished. C. The depth map is quantized to 4 layers. D. The depth map is quantized to 3 layers. Deblurring process. Patchy can be modeled as G sigma asterisk x where Zondier vectors, xi is the vector of the scene patch xx equals vec x, and sigma is the out-of-focus blurriness of sin y. The deblurring process restores xb. Where mu is a Lagrangian multiplier and d1 by 1 and d2 by 1 denote the discrete total variation of sin horizontal and vertical directions, respectively. The G sigma asterisk x can be represented as a matrix vector multiplication. 21, can be solved by an efficient variable splitting technique, as described in Ref.